So tonight's talk is very exciting, and I would like to introduce you to tonight's speaker. I'm pleased to introduce you to Professor Geeta Persad of the Jackson School of Geosciences here at the University of Texas at Austin. Geeta uses climate models, which are these complex numerical codes that simulate the entire Earth system in order to understand how the fundamental processes of climate change work. And in particular, she's an expert on aerosols, these particulates in the atmosphere, which play a very critical role in climate change. She's one of the leading authorities on that particular aspect of how the climate system works. I'd like to share with you that Geeta's background. Where did she come up with, this career path that she's on? Well, she went to a couple of good schools. She went to Stanford for her bachelor's. She went to Princeton for her PhD. But I think what's most impressive is that in my talking to her, I can share with you that much of her inspiration came from her K-12 education here in Austin through the Austin Area Homeschoolers Association. Let's hear it for the homeschoolers. Let's hear it for the homeschoolers, and let's hear from a rising star in the field of climate science, Dr. Geeta Persad.
Well, thank you so much for that introduction, Jay, and it is such an honor and a pleasure to be here with you all this evening, talking to you about something very near and dear to my heart, climate change science and climate change solutions. And I think when we hear the word climate change, it can feel very sort of abstract and vague and impersonal and kind of far off. So I want to take a moment and kind of start us all off thinking, kind of centering us in space and time. So let's really think about where we are, right? We're all here on this blue dot, this blue marble. We're actually right here on that blue marble. And this Earth has been here for a really long time, and it's going to be here for a really long time after we're gone. But we just inhabit this little spot in space and time here on planet Earth. And let's think about where we are in time, right? So we're here now, sitting here on the 2-year anniversary of the last Hot Science Talk, 2023. And I want everybody to think for just a minute about 2030, right? That's 7 years from now. If you're in middle school, maybe you're going to be thinking about where to go to college. If you're in college now, maybe you're thinking about what you want your career to be. If you're me, you're just trying to figure out how you're going to keep going for the next 7 years. No. Very exciting. And then think ahead to 2050. That's 27 years from now. What do you think your life is going to look like in 27 years? What do you think the world around you is going to look like in 27 years? Right? So really think about that. What are you going to be doing 27 years from now? So how many of you have heard about climate change in the news in the last week or something? Wow, everybody, oh my gosh. Yeah, we're all hearing about it in the news all the time. And how many of you have heard something like, we need to do this by 2030? Yeah, right? So think back to your view of yourself in 2030, right? And the world that you're told we need to be in 2030. And then how many of you have been told, this is what climate change is going to do to the world by 2050, right? We all hear that all the time. And I think those can feel like really abstract things. So I want to take a minute and just have us think about who we are going to be when that time comes. And what I want to do today is tell you how we've come to understand what we understand now about climate change and where things might be in 2050, but also the choices that we have now that are going to determine what kind of world we live in 27 years from now, okay? So to tell that story, though, we have to go back in time about the same distance to 1988, which is when I first showed up on this blue planet. And I showed up actually right here in Austin, Texas. I'm a born and raised Austinite, a very rare breed. So this was me back in 1988. And Jay asked me, when did you decide you wanted to be a scientist? And I realized I had kind of always been wanting to ask why. You know, I had been surrounded by all of this amazing inquiry right here in Austin. So I grew up going to the Zilker Botanical Gardens and wondering, you know, why is that leaf growing that way? I would go to the Texas Memorial Museum right here on campus and look at the dioramas of the way that, you know, dinosaurs used to walk the earth. I remember going out to the McDonald Observatory. How many of you have been out to the McDonald Observatory in West Texas? It's amazing. I remember driving up that mountain in my family's old Chrysler minivan and just watching the stars unfurl around me and just really wanting to know why. Why does the universe operate the way that it operates? And I was really interested in patterns. I wanted to understand what controlled the patterns in the world around us. I used to sit at our dining room table and look at the newspaper. I don't know if any of you remember the newspaper, but on the back of the newspaper, they had a map of the entire US and the weather patterns for that day. And I would sit there and I would look at that map and I would say, wait, why is it cold over here by the ocean? Why is it warm over here? Why is it raining there and not there? That's really as far as I got, though. I thought, okay, I want to know about patterns. I find these things really interesting. So I went off to Stanford for undergrad, and I was thinking, oh, maybe I'll think about patterns in astrophysics, or maybe I'll be a linguist and think about patterns in language. And that was when I took my first earth science class and realized, oh my God, this is where it's at. Earth science is how we understand the patterns in the world around us. Earth science is how we understand why the clouds look the way that they do. Earth science is how we understand why the mountains are where they are, or what the entire planet has looked like and why we're here, right? So I had that realization, and I want to tell you just a little bit of a story before we start getting into climate change, which can be kind of depressing, let's be honest, to the realization that I had when I took my first climate science class, which is that climate science is really fascinating and really powerful. So I used to spend all of this time when I was a kid just staring at maps like this. So I want everybody to just take a minute and look at this map and look at the patterns that you're seeing. And as you start seeing patterns, just kind of shout out, what are you noticing? What are the patterns that you see here? Ice? Yeah, where is the ice? Is it everywhere? No. The top and the bottom. Yeah, what else do you notice?
Brighter in the middle.
It's brighter in the middle. Yeah, you have these bands of brightness. Yeah, anything else? Well, someone has called out the thing that I used to stare at, which is those bands of brightness. It almost looks like somebody just took a paintbrush and did brush strokes of green and yellow and white across the planet, right, in these lines. Is that just a coincidence? Like, why does that happen? So those brush strokes of yellow are our deserts. Yeah, I heard someone say deserts. Those are our deserts, right? So why? Why are all of our deserts in this band? Turns out that most of our deserts are in this band around 30 degrees north and south of the equator. And climate science can tell us why our deserts are where they are. So I want to tell you guys that story. And it all comes down to where we are and where the sun is. So because our Earth is a globe, different parts of the planet get different amounts of sunlight. They get different amounts of energy. So here at the equator, we're getting a lot of energy. And at the poles, we're actually getting less energy. So why is that? Well, it's kind of the same as if you're shining a flashlight on a table, right? So if you shine a flashlight straight down on a table, all of that light is coming straight down to a small area. But if you shine a flashlight at an angle, that light gets spread out. And so that energy is getting spread out over a much bigger surface. And so each part of the surface is getting less energy. And that's exactly what happens on Earth. At our equator, we're shining the flashlight of the sun straight at the surface, so every part of the surface is getting a lot of energy. But then at our poles, that sunlight is coming in at an angle, and so everywhere's getting less energy. Now, nature hates that kind of imbalance, okay? Nature's always trying to get things kind of back into balance. And we've got all this energy in the middle and much less energy at the poles. And so our atmosphere, its main role is to redistribute that energy, to correct that imbalance. So one of the main reasons why we have wind and why we have weather is the atmosphere trying to get rid of those imbalances. And so if the Earth didn't rotate, our atmosphere would actually just be spending all of its time trying to correct that imbalance. And it would do that by taking all of this hot air right at the equator, rising that air up, and then moving it to the poles where it can bring that energy and correct that imbalance. And then that cold air would sink down and come back down to the equator to receive that energy again and then take it back to the poles. Now, does our Earth not rotate? No, it rotates, okay? And that actually does something pretty amazing. What it does is it actually turns all of the motion in our atmosphere. So in the northern hemisphere, that rotation actually turns all motion to the right, and in the southern hemisphere, it turns all motion to the left. And so what that means is that atmospheric circulation, right, it's trying to get all of that energy from the equator all the way to the poles, but it's trying to go along and it just keeps getting turned to the right, and oh, it can't get all the way there. So it gets all the way up to that 30 degrees north and it gets turned to the right, and it can't get all the way there. And so what that does is that it turns our atmosphere into these three cells. So the air's trying to go to the poles and then it gets cut off. And then it tries to go to the poles again and gets cut off. And then it tries to go to the poles and finally it makes it there. So we have these three cells in our atmosphere. And what that does is it creates this band of sinking air right here at 30 degrees north and south. And that sinking air makes it harder for thunderstorms to form and dries out the surface. And that's why we have our deserts where they are. It just so happens that the rotation of our Earth and the imbalance of energy between our equator and our poles creates this band of desert right here at 30 degrees north and south. Like, how cool is that? Like, science actually did just take a paintbrush and put those deserts there, right? So once I took a climate science class and I realized this, I said, okay, I gotta keep doing this. This is too cool to not do. So I decided I was gonna stick around in this for a while longer, and I spent a few years as a federal scientist with the National Oceanic and Atmospheric Administration, which is the federal agency that does a lot of the climate science in the US. And then I went and I got my PhD at the same NOAA lab where I had worked for a few years. And as I was learning more and more about this awesome climate science, I started to realize, okay, climate science is awesome, but it's also helping us understand this really massive problem. And that problem is one that kind of needs all of our energy. So what is that problem, right? So our climate system is awesome. It's making deserts, it's making ice, it's moving energy around. What's the problem? The problem is that our climate system is warming faster than at any time since human civilization and long before. And this is something that we know from observing our Earth. So here I'm showing you temperatures averaged over the whole planet going from today back to 2,000 years ago. And this comes from ice cores, from tree rings, from sediments, from all the ways that our Earth records the conditions that it's experiencing. And more recently, it comes from our own instruments, the things that we've built to measure temperature across the whole planet. And this band right here is showing you the range of temperature going back not just the last 2,000 years, but the last 100,000 years from those same records of the Earth. And you can see that the temperatures that we've reached in the last few years are unprecedented in the last 2,000 years and even in the last 100,000 years. Okay? And the other problem is that we can't explain this warming that we've seen without human activity, without human emissions of heat-trapping gases like carbon dioxide and methane. And this is something that we know from climate models, the models that Jay mentioned. And these are basically digital twins of the Earth system. We've taken everything that we know about the physics of the Earth system and we've put it into a giant piece of code. And it lets us ask those hypothetical questions. What if we hadn't emitted everything that we've emitted into the atmosphere? Would our climate system look the same way? And from those models, we know that it wouldn't. So this now is just zooming in on those 150 years, the most recent 150 years, and in black here is what we've actually seen, the warming that we've actually seen. And in blue is if we took our digital twin, our climate model of Earth, and we only gave it natural forces like volcanoes, changes in the sun, we wouldn't be able to recreate that warming that we've actually seen. But if we also give those digital twins our actual emissions, what we've also put into the atmosphere, that is the only way that we can recreate that unprecedented warming that we've seen. And we know that that warming and the carbon dioxide that we're putting into the atmosphere is already having impacts, right? So right here in the US, we've already warmed since 1970 by about 2.5 degrees, 2.5 degrees Fahrenheit. In Texas, we've warmed by about 3 degrees. And right here in Austin, we've already warmed by more than 3.5 degrees on average. So this warming is already here. We're already feeling the effects. And this is not just hotter days when we walk outside, right? It's actually also supercharging all of our extreme weather, our floods, our hurricanes. And climate science now tells us that events like Hurricane Harvey that hit Houston just a few years ago and caused massive floods was made 3 times more likely just by the heat-trapping gases that we've put into the atmosphere, and 15% more intense. So this is having real impacts already on people's livelihoods, on places that we care about. Austin alone has seen an increase in consecutive days over 100 degrees, which right now we're like, okay, that's not a big deal. But if you were around last summer in Austin, that's not a ton of fun. So we used to have very few of those days back in 1970 when my parents actually first moved to Austin. And now we're looking at, 10 to 15 straight days a year of 100-degree weather. Now, this is not just 10 days total. This is 10 straight days of 100-plus degree weather, right, that I'm raising. I have a 3-year-old right now, and trying to go outside when it's 100 degrees with a 3-year-old. Not a fun thing. And we're also getting more intense rainfall. This is already something that we're seeing even right here in Austin, right? So the rainfall that causes our floods, that damages people's properties, people's livelihood, that's already increasing as well. So this is the problem. But I actually think there's a lot of hope in this. So one of the things that I actually think is most hopeful about climate change is that we know about it. Imagine how much worse it would be if all of these things were happening and we had no idea why. And we also, therefore, had no idea that we could do something to prevent it, right? The fact that we actually know this is happening is one of the great triumphs of human knowledge, I think. So I want to tell you the story of how we actually came to know these things, right? So we know about how much we've warmed the planet by observing our Earth system, and we know that it's us that's doing the warming through these digital twins of the Earth system that we've built. And that's a big part of what I've done in my research. So I want to just walk you through the history of how we've actually done this. And this is a history that actually goes back a very long way. So back as far as 1824, and even before then, Jean-Baptiste Joseph Fourier first described that our atmosphere actually keeps Earth much warmer than it would be otherwise, and described it as a greenhouse. It's the same way that a greenhouse keeps plants at a nice warm temperature, even in a cold climate. Our atmosphere is doing that to planet Earth. And in 1856, Eunice Foote actually showed what it was in our atmosphere that was doing that heat trapping, carbon dioxide and water vapor. And a few decades later, Svante Arrhenius put 2 and 2 together and said, hey, actually coal produces a bunch of carbon dioxide, and all of that coal that we're burning as part of the Industrial Revolution that was well underway at that point is actually going to produce a bunch of carbon dioxide and heat up our atmosphere. Okay, so this was 100 plus years ago. And it was in the late 1950s that we started daily measurements of carbon dioxide in the atmosphere. And you can actually go to the website of the Mauna Loa Observatory, where we've been measuring carbon dioxide since the 1950s, and see what our carbon dioxide measurements are today. So I pulled this off 2 weeks ago or something, but you can go and see what it is today, okay? And it's risen from around 320 parts per million of CO2 in the atmosphere, which might not sound like a lot, but it's a really unprecedented amount, all the way up by about 100 parts per million. And I said this is unprecedented, and we know that from ice cores. So in the 1970s and 1980s, we started going out onto the ice sheets and drilling these ice cores. And in those ice cores are bubbles of air that preserve what the atmosphere looked like going back hundreds of thousands of years into the past. And based on that, we actually know how much carbon dioxide was in our atmosphere going back over hundreds of thousands of years. And this is showing you that the amount of carbon dioxide that we've put in our atmosphere now is almost twice as much as has been there over the last 800,000 years, which is well beyond when we even came onto this planet as a species. Okay, so these are really conditions that we've never seen. And that was something that we've known since the 1970s and 80s. Now, around the same time that we started measuring all of that carbon dioxide in the atmosphere, we started wanting to build a version of Earth that would help us really understand what that carbon dioxide was doing. And we couldn't run experiments on the real planet Earth, so we said, okay, let's build a digital planet Earth. And so in 1950, at the same institution where I did my PhD work, they built the first numerical weather forecast and actually forecast what weather was going to be doing over the next 2 weeks. And by 1975, so people didn't even have computers in their homes yet, we had a three-dimensional computer model of the entire Earth system that showed us that if we were to double the amount of carbon dioxide in the atmosphere compared to where it was before the Industrial Revolution, we would warm the climate by several degrees. So we already had the models in the 1970s that showed that. And by the 1990s to the 2000s, we were able to really demonstrate what I showed you at the beginning there, right? So this is showing you, again, in black, what actually happened to temperature, and in blue, what would have happened if only those natural forces had been acting. And in red here, it's showing you what happens when we have both human and natural influences. So this is what these digital twins allowed us to finally demonstrate, is that if we weren't emitting these heat-trapping gases into the atmosphere, we wouldn't be able to get the temperatures that we have now. And now we can run full three-dimensional simulations of the entire Earth system down to the scale of individual storms. So this is just showing you a snapshot from one of these models. And you can actually see volcanoes going off and spreading sulfur dioxide around. You can see dust storms swirling off of deserts. You can actually see industrial pollution coming off of India and China and the west coast of the US. So we can actually simulate our entire Earth system in incredible detail now. And that lets us really understand what would happen if we made different choices. What would happen to storms if we emitted less carbon dioxide? We can simulate all of that now with incredible detail with these models. And this is actually showing you simulations of the part of the climate system that I work on, which is aerosols, these particles in the atmosphere that, like Jay said, play a huge role in climate. And that includes things like dust, which is what you're seeing here in orange, but also industrial pollution. Some of the same things that contribute to smog, things like soot, sulfur dioxide, also contribute to climate. And that's what you're actually seeing in the greens and the whites here, is soot and sulfur dioxide flowing off of areas where we're burning forests or fields for agriculture, flowing out of areas where we have lots of transportation happening, lots of energy generation, all of these human activities. And so on this long journey from 1824, this was what finally hooked me in to this journey. And I want to just share with you one small piece of what I've tried to do to help give us more knowledge on this. So the same activities that emit heat-trapping gases also emit all of these toxic air pollutants that also affect climate, right? So all of those same activities that produce this smog that you might see in these pictures, right? So when we see a really dirty air, really bad air quality, climate scientists actually call those aerosols. We might think of it as smog. Climate scientists think of that as aerosols. And they're actually tremendously important for climate. But one of the things that's really important about those aerosols is that they're very different than greenhouse gases, the heat-trapping gases that we usually think about when we think about climate change. And they're different in some ways that actually matter for how we solve climate change. And so the main difference is that when you emit greenhouse gases into the atmosphere, these heat-trapping gases like carbon dioxide, it doesn't matter where you emit them. They go into the atmosphere, they heat the Earth system, and they cause all of those impacts that I talked about. But a big difference with these other air pollutants is that it really matters where you emit them. So if you take all of these other toxic air pollution that comes from those same activities that are producing those heat-trapping gases, and you emit them, say, in the US versus in China, you get really different impacts. Not only do you get impacts locally, but you get different patterns of impacts over the entire planet, right? And that really matters when we start thinking about how we're going to prevent some of these damages. And so what I've been using those digital twins, those simulations of the Earth system to do, is to understand how emitting these pollutants in different places is impacting our climate system. And so using these digital twins, we can actually see how emitting that air pollution from California versus emitting that pollution from Beijing, what is that doing to our temperatures? What is that doing to our rainfall patterns? And then we can translate those changes in temperature and changes in rainfall into the things that we really care about, right? Things like our public health, things like our food security. And so we can actually use these models to make these maps like these that tell us the global benefits to things like infant health from cutting those air pollutants in some of the big countries that are producing those pollutants. What are the benefits to agriculture? And one of the things that we've been able to do with these calculations is look at things like how much benefit do we get from cutting not just the carbon dioxide and the greenhouse gases, but also these other toxic air pollutants. And so if we take the amount of benefit that we get just from cutting these greenhouse gases, it's already a huge benefit, right, to prevent some of those impacts I was talking about. But then if we also add on the benefits that we get from cutting those other toxic air pollutants, in the US, that increases the benefit that we get by about 50%. But for a place like China, it actually increases it by about 400%. And in a place like India, it increases it by about 800%. So this means that the benefits that we get from climate action are even bigger, right? And this means that there's even more incentive to act. Okay, so we have a problem. It has impacts. The solutions are worth it. So how do we actually get there, right? How do we get there? Well, first we have to think about where all of these pollutants are coming from. They're coming from our energy sector. They're coming from our agriculture and our food systems. They're coming from our waste systems, from our industry, right? These are big systemic sources of our pollution. But there is a lot that we can do right now to cut these emissions. And I know that we all wonder, right? What can I do to solve climate change. Like, what can I do to cut these emissions, right? And there's lots that we can do individually to cut climate change. But what I actually want to focus on is what we need to do as a society and what you can do to help us do what we need to do as a society. And that's this, which is speak up. Because if we think about where these emissions are coming from, these huge systemic sources, our entire energy system, our entire food system, right? Individual action is important, but what we really need is collective action. What we really need is action as a society. But that can come from the individual action of talking about climate change. And let me just show you why that is. More than half of Americans in almost every single congressional district are worried about climate change. Okay, this is from a poll that was done by Yale in 2021. They do this every single year, and every single year it's been getting higher and higher. But we always underestimate how much other people care about climate change. And I'm just going to show you an example of this from a paper that just came out this year. So I'm showing you two values here of what people report on a survey about the idea of being worried about climate change. Okay, so we've got this black square and then we've got this red line. What are those two? Well, the black square is how much we think other people are worried about climate change. And the red line is how much we actually report that we are worried about climate change. Okay, so we think everybody else is way less worried about climate change than everybody actually is. Most of us are worried about climate change, and we think that most people are not. And this is true of a bunch of different things. It's true of how much people support a carbon tax that would put a price on carbon dioxide emissions and make it easier for us to incentivize cutting those emissions. It's true of things like building more renewable energy on public lands, even getting to 100% renewable energy by 2035. Most people support these things, and most people think that most people don't support these things. And that's because we're not talking about it, okay? And this is why talking about it is actually one of the biggest things that we can do to help fight climate change as individuals. So good job, all of you, for being here. You're taking the first step towards it. And the really important thing is that we actually have the technologies already to make meaningful progress in slowing down climate change. So I'm going to show you just a few examples that each could cut percent off of the amount of carbon dioxide that we put into the atmosphere, each individual thing, while also saving trillions of dollars and using technology that we already have. So 1/3 of food purchased worldwide is wasted, and if we could eliminate just half of that waste, that would make a huge benefit because it would reduce the amount of waste that ends up in our landfill and decays and puts heat-trapping gases into the atmosphere. Okay, and that would save us billions of dollars. If we were to increase solar power to meet just 20% of our electricity needs worldwide, that would make a huge dent in cutting our heat-trapping gases. If we were to replace just 30 to 40% of urban transit with public transit, with technologies that already exist, that would cut 50 to 100 gigatons of carbon dioxide from going into our atmosphere over the next 30 years. Refrigerators are actually a big source of heat-trapping gases, which is a little bit confusing. But our refrigerators and our air conditioners actually have a kind of gas in them, hydrofluorocarbons, that trap heat. And when those refrigerators go to the landfill, they start leaking, they break down, and all of that goes into the atmosphere. If we could just eliminate those leaks, we could make a massive dent in climate change over the next 30 years. If we were to scale up onshore wind power from 4% to 20% of our electricity demand, we would make a big dent. And if we were to use technology that we already have available to plug all of the leaks in our natural gas infrastructure, using technologies that would actually save money for the natural gas industry, that would make a huge dent in cutting climate change. So all of these are things that make meaningful progress on solving climate change while also saving money. And you'll notice there's no one single solution, right? There's a grab bag of different solutions that we have to choose from. And I think that's really important because every single bit of climate action matters, right? So you might hear people say, well, there's so much that we have to do to prevent climate change. There's no way we're going to do it all. Why should we even bother, right? It's just too hard. But the reality is that every little bit of climate action matters. So this is just showing you different trajectories that we might end up on, right? So remember that idea of 2050, 27 years from now. What does that world look like? If we weren't to do anything, we would easily get to about 4 degrees centigrade of warming worldwide. And that's where we start to see really big impacts on things like our food security, on our biodiversity, on so many things that we care about on our planet and our way of life. And a really ambitious goal that's been set by the international community is to make sure that we don't get past 1.5 degrees of warming. And a lot of people say, oh my God, this is so hard to get to. There's no way we can do that. Why are we even bothering talking about this? But that forgets about all of this in the middle, right? Everything that we can do to prevent this world and get ourselves as close as we can to this world is worth it. I also want to highlight, you don't all have to be me to help solve climate change. That would be super boring, right? You can do whatever you want and still help fight climate change. There's an amazing initiative that's been started by a group called Project Drawdown that really is trying to point out that every job can be a climate job, right? So maybe you want to be an engineer or technician. Maybe you're already an engineer or technician, right? You can build climate-safe infrastructure. You can help develop the technology for these climate mitigation solutions. Maybe you want to go into finance, or you're already in finance. You can help build the funds that are going to help incentivize these solutions. Maybe you're in marketing, right? You can help make climate action cool. If you're an artist, you can help us tell the story of what that climate-safe future looks like. You can help inspire people for what we want the world to look like in 2050. And just last year, I had the tremendous honor of being at a roundtable just like that at the Sundance Film Festival, where we were calling on artists to come to the table and help solve climate change, right? You might not think an artist has a role to play in climate change, right? But imagine if we could see the vision of what a climate-safe 2050 looks like, how inspiring that would be, right? So there's a role for everybody in solving climate change. So I want to close by just taking us back to this idea of time, right? We're sitting here now in 2023. There's so much we have to do to make the world that we want to make in 2050, but it's worth it. And we have the solutions that we need to get there. So thank you so much for spending your evening with me, and I'm so excited to see what you all bring to the climate change solution. Thank you all.
Thank you so much, Geeta. And we have time for lots of questions. And so if you could advance one more, I think we'll
Sure.
pull up yeah, so there you go. If you want to ask questions, we already have many in here. But please go ahead and ask your questions. So maybe we'll start with, and feel free to list your name because if it's an extra good question, you might qualify for a door prize when you post your question. So first question is, do the heat-trapping gases stay in our atmosphere or do they eventually go away?
It depends on what you mean by eventual. So one of the big problems with climate change is that these heat-trapping gases, most of them stay up there for a really, really long time. So carbon dioxide stays in the atmosphere for hundreds of years. Methane is a little bit better. It stays there for a few decades, but I don't know, a decade is a pretty long time. And so that's one of the issues, right? Every ton of carbon dioxide that we're putting into the atmosphere right now, we're going to be stuck with for hundreds of years. And so that means that even when we stop emitting, we're still going to have all of this heat-trapping gas in the atmosphere. And that's part of why every bit of climate action matters, right? Every ton of carbon dioxide that we can keep out of the atmosphere is really important because it's going to stick around there for a really long amount of time.
Excellent. The next question, can we reverse the damage that we have done or only prevent more damage in the future?
This is a really good question. We can definitely prevent more damage in the future. And I think really importantly, we can do a lot to help mitigate, to help reduce the effects of the damage that's already happened, right? So when you think about the impacts of sea level rise on a community, sea level rise is a very slow-moving process, and all of the heat that we've already put into the climate system has already baked in a lot of sea level rise. But there's so much we can be doing to help protect communities from sea level rise, right? And so even if we can't reverse damage that's already happened, we can invest in making sure that those damages don't hurt the people in the places that we love. So I think that's the thing to really focus on.
Right on. Next question, how do we encourage other countries to help prevent climate change too?
Yeah, this is a really good question. And I actually think a lot of countries already are really invested in solving climate change. But that was actually a big motivation of the research that I did, trying to think about all of the other stuff that we put into the atmosphere when we emit heat-trapping gases, right? So like one of the issues with carbon dioxide is everybody emits it and everybody feels the impact. So if you don't turn down your carbon dioxide, why should I bother turning down my carbon dioxide? But with these toxic air pollutants, if I turn down my toxic air pollutants, I get health benefits right away. I get agricultural benefits right away. And so that's actually been one of the big things that's been helping incentivize climate action across the world, is people realizing, oh, hey, if we do this climate action, not only do we help prevent climate change, we also get all these other benefits as well. So why wouldn't we do that? So that's actually been a big part of encouraging countries everywhere to commit to climate action.
Well, this one's interesting. Within your climate models, what are some of the biggest limitations or uncertainties, and how are you working to improve them? Maybe this is from an editor or reviewer at Nature Geoscience.
Maybe, yes. So remember I talked about how climate science can help us understand why clouds are where they are? Clouds are actually one of the hardest things to simulate in a model. And you can think about that if you look outside on a cloudy day, right? Or like on a kind of half cloudy, half blue sky day, which we get lots of here in Texas, right? There's all these different types of clouds. There's like a big puffy cloud over there, and then there's a thin one up there, and this one was here 5 minutes ago and now it's gone. And so you can imagine what it's like to actually try to simulate that across the whole planet at every moment of every day. And those clouds are actually really important because they're bright. They reflect a lot of sunlight back out of our climate system, and they cool the climate system. And so if we're not getting the clouds quite right, we might not be getting their cooling effect quite right. And so that's actually one of the biggest things that we're working right now to try to figure out in climate models. And one of the ways of doing that is just building fine climate models that can get us down to cloud scale, that can actually simulate individual clouds, and that's like one of the big new frontiers.
Neat. How accurate were the models that were made in the 1970s? Are they identical to what actually happened in the atmosphere?
Oh my God, that is a really good question, and also a mind-blowing one because they were actually incredibly accurate. So in the 1970s, we were building these models and projecting into the future, and our carbon dioxide emissions haven't followed it exactly, but if you correct for that change in how much carbon dioxide we actually emitted compared to what they thought we were going to emit, they simulate what actually happened almost exactly in terms of what happened in terms of our global average warming. And that is incredibly fascinating that they were able to get that right in the 1970s.
It's remarkable. Which countries or places are contributing to this problem the most? Are there certain places doing considerably more damage than others? Who are the bad guys?
Who are the bad guys? Man, everybody wants to know the good guys and the bad guys. So their climate change, carbon dioxide, because it lasts in the atmosphere for a really long time, creates a really interesting problem. because there's the people who are emitting a lot of carbon dioxide now, but those are different than the people who have been emitting a lot of carbon dioxide in the past. So do we blame the people that emitted all the carbon dioxide in the past, or do we blame all the people that are putting carbon dioxide into the air now, right? That's a big question. And then, I don't know about you, but I'm pretty sure all of the emissions that went into making this weren't here, but I bought this. So am I responsible for all the emissions that happened somewhere else to make this? Or are they responsible for it? So I think this question of who is causing climate change is kind of pointless. That's my answer to that question. Yeah.
Well done. So there's a lot of interest about food waste, and any recommendations you have for how we reduce that waste?
Oh man, I am probably not the best person at UT to answer that question. I hope there are lots of people doing good work on this. Don't have a 3-year-old. That's one answer to that question. Yeah, I wish I had a better answer.
Okay.
I don't.
This one is, I think this one's going to be right in your wheelhouse. You mentioned that aerosols emitted in other countries can affect other places around the world. Why is this? Wind?
Oh, yes. So it's because the atmosphere is all interconnected. So one part of it is wind. So you emit these aerosols into the atmosphere. These aerosols actually stay near the surface because they're particles, they're not gases, and so they get carried by the wind. So some of it is that. So it's going to be carried by the wind to a different place if you emit it in Beijing versus if you emit it in New York. But then also the atmosphere is all connected. So if you take those aerosols and you heat up the atmosphere in one place, the atmosphere is going to say, hey, that area is hot. I don't want that area to be hot. I want to take that heat and put it somewhere else. I want to spread it out. And so that actually causes its own atmospheric motion. And so depending on where you put that heat, say in the atmosphere, it creates its own specific pattern of atmospheric motion that then changes rainfall patterns in a specific way and gets incredibly complicated. And that's why I have a job.
That's where you come in, I was
Yeah.
just going to say. This question comes from Matthew Guthrie. I saw an article saying the ozone was repairing itself. Is that valid?
Yes, so the ozone hole is actually one of the big successes in our ability to realize through science that our emissions were causing a problem, come together as a society and solve it. So this actually was something that was detected in the 1980s, that we were actually emitting these pollutants that were causing this ozone hole that had all of these impacts on human health. And so we came together internationally and said, okay, we're going to shift away from these pollutants and we're going to find alternatives. And we did that, and we brought down the emission of those pollutants, and now our ozone hole is recovering. So it's actually an amazing success story of what we can do when we have the science to recognize the problem, have the solutions, and come together as a society to do it. We can do it. We've done it before. So it is valid and encouraging.
Which leads to the most popular of the questions based on how many likes it's got. Do you think we can engineer climate to tackle climate change?
Now, this is a very interesting question. I think the answer comes down to how well we think we have engineered climate so far, right? I don't think we've done a particularly good job of engineering the climate so far. And we know that it's had a massive impact. And I think one question is, if we tried to engineer the climate like a really finely tuned machine, how would we even know that we were getting it right? The climate system is so complex. And so we know that greenhouse gases are the problem. We know that if we reduce greenhouse gases, we will reverse that problem. But I think to think that we can fine-tune some other engineering solution is kind of hubris. That's my answer to that question.
Right on. What is the best approach to encouraging the oil industry to battle climate change? Is it a carrot or a stick approach more productive?
If I knew the answer to that question,
We'd be done.
we'd be done. Yeah, I think that I can only answer that question as a human being, not as an expert on, business policy, to say that the oil and gas industry is made up of human beings, and they all live on planet Earth, and they're all feeling these impacts and will be feeling these impacts. And so I hope they can recognize that they're going to be part of this as much as all of the rest of us.
Right on. Martin asks, is the rate of climate change speeding up?
So the short answer is yes. The long answer is that the climate system has been doing things long before we came around, and then we came around and started pushing it in one specific direction. And the climate system likes to kind of go this way, and then go that way, and then go this way. And so we started pushing it that way, and so it goes this way, and then it goes this way, and then it goes this way, and then it goes this way. And so it's kind of still doing that, but it's also accelerating. So every now and then it kind of slows down a little bit because it wanted to go back that way, but then it just keeps accelerating again. So overall, the climate system is the warming is accelerating. Every now and then it kind of slows down a little bit, and then it keeps going. But when we look over really long time scales, it's clearly accelerating.
Another interesting thought question. How can one make skeptical people believe about climate change?
So for anybody in the audience who has not been exposed to the work of Katharine Hayhoe, I really encourage you to go and check her out. One of the things that she has so she's a climate scientist like me. She comes from the evangelical Christian community, and one of the things that she is really focused on is this idea of meeting people where their values are. So we all have different reasons why we would care about climate change. And her goal is to really understand what do people value and try to meet where you have common values. And that's really the place where you can help people recognize where they should care about this issue and how it can be consistent with their values. So I really encourage you to check out her work. I see some of her books over there, so I think some people are going to get a preview. Katharine Hayhoe, Hayhoe.
One of the door prizes is a book by Dr. Hayhoe. You'll see it in detail in a second. So this question is, this is an interesting one maybe to finish on. It's obviously typed in by an adult, says it comes from a young member of the audience.
Ooh.
Will the earth be destroyed?
Oh, no, at least not by climate change. Maybe by something else, but not by climate change. The earth will be here. Someone once asked me, oh my God, is climate change gonna mean that we all die? And thankfully, I think the answer is no. And I think there's a lot we can do now to make that answer very, very, very much no. So no, the earth is not going to be destroyed, and you will still be able to go outside and enjoy the parks and enjoy the wildlife, and there's a lot you can do right now to make sure that that stays true.
So in sum, do you consider yourself optimistic or pessimistic?
I have a 3-year-old. I have to be optimistic. I'm incredibly optimistic. I think this is where I come back to with being a climate scientist and the fact that we know this is happening. That is just so amazing to me that we as a society have developed enough to the point that we can actually see this problem coming and devise the solutions to it. That is I know we caused the problem, but we also know about it and can solve it. And I think that's actually a tremendously hopeful thing. So I'm an optimist.
On that note, let's thank Geeta for an amazing talk.
Thank you all.